Hello class, welcome to SciChem. Here we are for another session of lecture number 2 of second unit of phase equilibrium. In the previous class, we have already discussed about what is Gibbs-Duhem-Margulis equation. Now we are going to discuss about the application of Gibbs-Duhem-Margulis equation, that is fractional distillation of binary solution. So what is fractional distillation? So what is fractional distillation? So fractional distillation is the separation of mixture into its component parts or fractions. Chemical compounds are separated by heating them to a temperature at which one or more fraction of the mixture will vaporize. So what is the concept behind this? Let us consider we have a binary solution. Consider a mixture of water and alcohol, and we know water have boiling point, that is 373 K, and alcohol have boiling point 353. So we have taken the mixture here, water plus alcohol is our liquid phase. So simply we have to heat this mixture. Upon heating, water have boiling point 373 K, whereas alcohol have boiling point 353 K. When we reach the temperature, when the temperature is 353 K, then the alcohol molecules will be evaporated or escape the liquid phase and converted into the vapor. If these vapors are being cooled, then we find pure alcohol. And this is the basic behind fractional distillation. Fractional distillation is based upon the boiling point temperature of the individual components. Here we have taken two components, that is water and alcohol. Water have 373 Kelvin boiling temperature and alcohol have 353 K boiling temperature. So by simply heating the mixture, we found that the alcohol first boils and converted into vapor. If we collect that vapor and cool down, then we can find pure component of alcohol. So we can easily separate alcohol from water mixture. So this is the basic behind fractional distillation. So we have to study fractional distillation for binary solution. Binary solution means we have to take two component system, that is one is solute, another is solvent, where solute and solvent both are in liquid phase. Solute and solvent both are in liquid phase. So we have to study fractional distillation of binary solution, that is ideal or non. So this ideal binary solution, what is ideal binary solution? The solutions which obey Raoult's law, the solution which obey Raoult's law are called ideal solution, and the solution which does not obey Raoult's law and shows positive and negative deviations are called non-ideal solution. So fractional distillation of binary solution having ideal solution is also called geotropic mixture, and for non-ideal solution it is also called ageotropic. So geotropic mixture and ageotropic mixture. For ideal solution that is called geotropic mixture, and for non-ideal solution it is called ageotropic mixture. So first we are going to study what is ageotropic mixture. So ageotropic mixture, another thing, important thing is there. When fractional distillation is possible, let us consider this is our liquid phase. So liquid phase have mole fraction, consider XH2O, and alcohol have mole fraction XC2H5OH. This X is also called chi. When fractional distillation is possible, so total mole fraction equal to 1, total mole fraction is equal to 1, mole fraction of water, mole fraction of alcohol is equal to 1. So let XH2O and XC2H5OH is the mole fraction in the liquid phase, and YH2O and YC2H5OH is the mole fraction in vapor phase. Since upon heating water also boils and alcohol also boils, so some amount of water is also present here, some amount of alcohol is also present here. So total mole fraction will be 1, but let us consider YH2O is the mole fraction of water in vapor phase, YC2H5OH is the mole fraction of alcohol in vapor phase. When fractional distillation is possible, when XH2O is not equal to YH2O. When fractional distillation is possible, when XH2O is not equal to YH2O or XC2H5OH is not equal to YC2H5OH. That means if we are considering fractional distillation, then the mole fraction of a component in vapor phase should not be equal to the mole fraction of component in liquid phase. Then only the fractional distillation is possible. But since we are considering ageotropic mixture, so ageotropic mixture is also a binary solution having solute plus solvent. Consider it is our P. Both are in liquid phase. They have fixed composition of solute, and they have fixed composition of solute and solvent. They boil at constant temperature, and for ageotropic mixture fractional distillation not possible. Ageotropic mixture fractional distillation is possible. Why fractional distillation is not possible in case of ageotropic mixture, that is up to non-ideal solution? Because when fractional distillation is possible, when mole fraction of XH2O and should not be equal to YH2O, since we are considering two component, that is A and B, here A plus B is present in liquid phase, here A plus B is present in vapor phase, is our liquid phase. Why fractional distillation is not possible? Here XA is equal to YA and XB is equal to YB. When fractional distillation is not possible, or why fractional distillation is not possible? When the mole fraction of the component in the liquid phase is equal to mole fraction of the component in the vapor phase. If the mole fraction of a vapor phase and the liquid phase is same, then fractional distillation is not possible. And this case arises only when they have a fixed composition of solute and solvent. It does not arise regularly, but we have to consider a fixed composition of solute and solvent. So in general, azeotropic mixture can also be defined as an azeotropic compound is a mixture of two substances which distill at the same temperature. That means constant boiling. That means both A and B boil at the same temperature. But what happens here, normally in case of fractional distillation, due to boiling point temperature difference, they will boil at a different temperature. Water boil at 373 K, but alcohol boils at 353 K. But if we are considering a fixed composition of a solute and solvent, then at that fixed composition, the solution or mixture will boil at a constant temperature. An azeotropic is a mixture of compounds with the same composition in the vapor as well as in the liquid. In other words, an azeotrope is a liquid mixture that has constant boiling point and whose vapor has the same composition as the liquid. Several compounds such as toluene, benzene, cyclohexane form suitable azeotropes with water. So now we are going to study about types of azeotropes. Types of azeotropes. Types of so azeotropes, it is of two types. It is types of azeotrope, it is of two types. That is minimum boiling azeotropes, another is maximum boiling. For this, consider minimum boiling azeotrope. Consider example of 95% C2H5OH solution, and for maximum boiling azeotrope we have to consider 68% HNO3, 68% HNO3 solution. So what we are considering here, for minimum boiling azeotrope we have to consider 95% C2H5OH solution, and for maximum boiling point we have to consider 68% HNO3 solution. 95% C2H5OH means if we are considering 100% of the solution mixture, then there will be 95% of alcohol and 5% will be water. And similarly, if we are considering 68% HNO3 solution, that means there is 32% of water and 68% of HNO3 component. So consider, since these are non-ideal solution according to Raoult's law, here I am taking the mole fraction and here I am taking the vapor pressure. So what happens here, just see, since consider this X C2H5OH equal to 1 at this point, X C2H5OH is equal to 1 and XH2 equal to 0. Here XC2H5 at this point, XC2H5OH equal to 0 and XH2 equal to 1. So here alcohol is present, that is pure component. Here water is present, that is pure component. So boiling point of water is more, since so I have given this point. and alcohol have less boiling point as compared to water considered. So according to Raoult's law, I can draw the graph like draw the graph, and this is for ideal solution. But this type of solution, 95% C2H5 solution, this type of solution show positive deviation. Since they show positive deviation, I can positive deviation. That means when the mole fraction of alcohol is 1, they have boiling point here. When the mole fraction of water is 1, they have boiling. If I am changing the mole fraction, that means consider here alcohol is present 100%. When I am changing this here, that means at this point represents 95% alcohol and 5% of water. So they have maximum vapor pressure. At that point, they have maximum vapor pressure. That means this is the azeotropic composition. This is the azeotropic composition at which they have maximum vapor pressure. That means both the vapors of alcohol and water can be found at this composition. So they have maximum vapor pressure. If I have to draw the same type of graph, here I have to take temperature, here I have to take mole fraction. So this is the consider boiling point of water, and here boiling point of alcohol, this point. So if I have to consider same composition, 95% alcohol, since at 95% composition of alcohol the vapor pressure is very high, that means vapor pressure is inversely proportional to boiling point. Since at this composition vapor pressure is very high, that means at this composition the boiling point of the liquid will be very low. So the boiling point will be very low. That means the mixture will be boil less than that of, consider this temperature, this is the 353 K, and this is 351 K, and this is 373 K. So since the vapor pressure at 95% composition is very high, that means at that composition the boiling point of the solution or boiling point of the mixture is very low as compared to individual component. Individual component means the boiling point of alcohol is 353 but water is 373, but the 95% composition have a boiling point is 351 K. That means the boiling point is further decreased. This type of azeotrope mixture is called minimum boiling azeotropes. So by combining, I can also draw this type of graph. So similarly, for maximum boiling azeotrope, consider 68% HNO3 solution, and this solution show negative deviation. Negative deviation. Negative deviation means so negative deviation means sorry H2. X water have boiling point 373 and HNO3 have below, that is the boiling point. Since the solution show negative deviation at 68% composition, 68% composition, that means 68% HNO3, they have less vapor pressure. The smooth curve. So at this composition, 68% composition, they have less vapor pressure. Why less vapor pressure? Because they show negative deviation. Since they show negative deviation, so they have less vapor pressure. If I have to consider with respect to temperature and mole fraction, then I can find graph A. At this composition, they have maximum boiling point. So vapor pressure is low, so boiling point will be maximum. So this is all about azeotropic mixture. So for azeotropic mixture, we cannot fractional distillate the two types of solution. The fractional distillation is possible only when the fractional distillation is possible only when the mole fraction of the vapor phase is equal to mole fraction of the liquid phase. Could not be equal to liquid phase. If the mole fraction of vapor and liquid phase are equal, then the fractional distillation will not be possible, and that type of solution are called azeotropic solution or azeotropic mixture. Azeotropic mixture is also two types: minimum boiling azeotrope and maximum boiling azeotropes. So now we are going to discuss about geotropic mixture. Geotropic mixture is also called fractional distillation of binary ideal solution. Fractional distillation of binary ideal solution. So let us consider a binary solution. A plus B, and this is their vapor phase. So here I can write YA consider this is the vapor phase YA and YB. YA have composition 30%, consider is 70%. Similarly, XA, XB, XA have composition 90, 10. So for a geotropic mixture, what happens? Consider two components. A is more volatile than B. Since A is more volatile than B, here I have taken pure B, here I have taken pure A. So A is more volatile means it have low boiling point, it have higher boiling. So this is the curve for vapor phase, and this is the curve for liquid phase, and in this area vapor and liquid both exist with each other. So B, here B is 100, A is 0, here B is 0, A is 100. So let us consider at a certain temperature, it is temperature versus mole fraction. At a certain temperature, this temperature, consider this X. At a certain temperature, when we heat the mixture, at a certain temperature X, when we heat the mixture, we are heating the mixture at a certain temperature X. So it's chi, it is X. At a certain temperature, when heat the mixture, at a certain temperature, when we heat the mixture, it have been found that the mole fraction of component A is 90% and component B is 10% in liquid phase. So since this curve is represented for liquid phase and this curve is represented for vapor phase, so liquid phase have composition that is 90-10%. 90-10%. And for vapor phase, it is found that 30-70%. 30-70%. So at a temperature when we heat the mixture, liquid phase have composition 90-10, whereas vapor phase have composition 30-70. So at same temperature, the component in liquid and vapor phase is different. That means at the same temperature X, the component in liquid phase is different, component is vapor phase is different at a same temperature T. Such kind of temperature at which two different types of composition exist for liquid phase and vapor phase are called geotropic mixture. Such composition is also called geotropic composition. So this is geotropic mixture and the composition is called geotropic composition. So this is all about the fractional distillation of geotropic mixture and ageotropic mixture. For geotropic mixture, we can easily separate the component, but for ageotropic mixture, we can not easily separate the individual component from the mixture. But for geotropic mixture, we can easily separate. For geotropic mixture, we have to consider the ideal solution, binary ideal solution. They do not show any positive or negative deviation. Why geotropic mixture can be easily separated to individual component? Because at a certain temperature T, the component in liquid phase, the component is liquid phase is 90-10, whereas the component in vapor phase is different. Since the component of liquid and vapor phase are different, that means we can easily separate the liquid. So consider this vapor when we cooled this composition 30-70. That means here A is present in 30% and B is present in 70%. This is the vapor when we cooled. We found the liquid mixture of A plus B, in which A is present 30% and B is present 70%. When we heat that mixture, then when we heat that mixture, what will happen? Is A plus B? A plus B. Since B is 70% present, that means when we heat this mixture, this vapor phase composition having B percentage is greater than 70. B percentage is greater than, and A percent is less than. So in this method we can easily separate or easily fractional distillate to find a pure component. So this is all about geotropic mixture and ageotropic mixture. So thank you.